Ladies and gentlemen, we have picture, and we are back on the computer, although with help, of course. Turned out, though, that the problem in this case was the cable. So just to show that it's not just wireless connections that give problems. In this case, the reason that I didn't get a picture from my laptop is because the VGA cable is broken, and you need to bend it just so to get a picture. OK. That means that we can quickly go through the presentation. Most of it we have already seen. So we discussed this. We discussed the various decompositions, right, into smaller parts. And one thing that I did not discuss at that time, but which might be important at some point, is that there are two things that are related but not the same. One is that you can decompose a system into multiple transceivers, and a transceiver into multiple circuits, and a circuit into multiple components. But that's just decomposition. That takes the whole thing, and you just conceptually using a scissors, you make it into smaller parts. You cut it into smaller parts. What very often happens in parallel, but which is a different dimension, is that the description of the thing that you're talking about changes from more abstract to more concrete, to more physical. Right? So if we talk about the whole system, very often we talk about it in terms of specifications, a functional model. We only tell what it should do, not how it does it. But we could also talk about the wireless system as a structural model. How is it composed of all its subcomponents? Or even a physical thing. Right? What does it look like? We have all these transceivers. And usually we do these things at the same time. So usually we decompose into smaller parts and smaller parts. And at the same time, we go from conceptual abstract levels to more precise descriptions in terms of physical models or even measurements. In this direction, going from top to bottom, we go through a hierarchy. And that means that we basically decompose the system into smaller parts. And in this direction, we go to abstraction. We have either a more abstract way of describing what we're talking about, and or a more concrete way, a more detailed way. And there are orthogonal dimensions, but they are often used or traveled through simultaneously. But it's good to know the difference. This we discussed, right? So the 4 steps, also the part that we did before, and the part that we are going to do today, going from transceiver specs to circuit specs. It's a creative process. That means there's no single perfect answer. Although in my thesis I tried to give, for example, this optimum gain distribution, there's still a lot of things that basically a designer has to decide and to come up with inventive and creative solutions. So that means that even if multiple teams do the same design, they very likely will come up with different solutions. And that's also the nice thing about this course. That also means if there's multiple teams of students and they get the same assignment, it's perfectly acceptable and to be expected, in fact, that you come up with different solutions and that all of them are good or bad or whatever you do, right? But it's not necessarily said that only one can be right. And that's one of the things that makes RF design so nice, because it's not like you take a cookbook and you go through the steps and you all come to the same answer. No, there's really a lot of room for creativity in each of the steps, in making the system specification, in choosing the architecture, and in designing the circuits. So we also talked about gain, noise, and linearity trade-offs, and frequency conversion and selectivity trade-offs. Frequency conversion, we talked about this, right? The small wanted signal and the large interferers, and the quality factor of the filter that you have here versus the quality factor of the same bandwidth filter at a lower frequency. And this one is a lot easier. And the reason why I talk about easy and difficult is that if you have a filter here with a high quality factor, if you implement that filter, you basically have two choices. You either implement it using passive components or active components. If you implement it using passive components, then the quality factor of the filter can never be better than the quality factor of the worst passive component. Now let's look at some numbers. Let's say that we have here a frequency of 10 gigahertz and we want to select a 1 megahertz wide channel, 1 megahertz wide transmitter. We need a quality factor of 10,000. If you do that with passive components, with inductors and capacitors, in mainstream technology, in CMOS technology that you will be using for the assignment, the best quality factor you can get for an inductor at these frequencies is around 10. So there's no chance in the world that you can make this filter using a passive design at these frequencies. If, however, I shift all these signals to a low frequency, let's say around 5 megahertz, and I want to select only 1 megahertz wide, so the bandwidth is still the same, but the center frequency is now very much lower, so my quality factor is much lower, it's now only 5. That filter I can build using quality factor of 10 components. And so that's the whole point of moving to a lower frequency. It allows you to implement filters here that you could never realize with the same quality of components at a higher frequency. And we already discussed that if you have this circle with 2 lines in there, which is basically multiplication, that you can get this frequency shift implemented, and that you get free of charge also another component at double the frequency, which you don't want, and which you have to filter away. There's a few things I want to point out. One is that I showed it in the first lecture hour with sines. That was wrong. It should have been with cosines. With sines, you get almost the same answer, but with slightly different plus and minuses. So my apologies for making that mistake. But I'm not very good at doing all the fine mathematical stuff. I always use a calculator or computer program for that. But essentially also with sines, you get the sum and the difference. And with the cosine, you get exactly this. One of the things that I had expected at least one of you to say, because you're all critical students, right? You're expected to be extremely critical. So one question could be, why do you multiply? Why don't do something else? Why don't you add or divide or something else that gets you this frequency shift without getting this extra component? So anybody who wants to ask that question, or some of you who have already the answer to that question? If you think about frequency conversion, what kind of operations can we consider? Why do we go to multiplication? Could we do addition, for example? Could I just add this signal to that signal and then expect the output to be shifted in frequency? No. Because any linear operator has the same output spectrum as input spectrum. Output frequency components, I should say, as input frequency components. There's no frequency shift possible. At least if it's linear and time invariant. So obviously we need something that's nonlinear. Now the good thing is many, many things are nonlinear. In fact, just about everything is nonlinear if you try hard enough. If you make your signal large enough, anything becomes nonlinear. And even if you don't believe that, we still have this building next to Potential, right? The high voltage building. Even if you take a perfect wire above a ground plane, you think it's perfectly linear, well, just put 1 million volts on it. People can do that there. And you can see you get sparks all over the place and your linearity is gone. Right? Everything becomes nonlinear if you push it to the extreme, at least anything physical. Pure linear things only exist in models. Nevertheless, we need something nonlinear, and so many things are nonlinear. And anything that's nonlinear, you can model, you can describe using a Taylor series. Right? You can describe as a polynomial that says the output voltage is the input voltage times some coefficient plus the input voltage squared times some other coefficient times plus the input voltage to the power of 3 times yet another coefficient, and so on. So that means that any nonlinear component has in it a linear part, a square part, a quadratic part, a third order part, and so on. And when you do the calculations for the output components that you get out of such a Taylor expansion, then these components are always in there. So you have two choices. You can either believe in something linear, and despite the fact that you can't have it in reality, but even if you could have it, it would not give you a frequency shift. And if you have something non-linear, it does give you a frequency shift, but you always get this for free. So you might as well do multiplication, because that's the easiest form of nonlinearity. But in fact, anything that's nonlinear will allow you to do frequency shift, and each of them will give you this problem. So you have this, and we can look at that in the diagram. We have this system where we have a wanted signal, and we have an LO signal that we want to use to shift this green signal to this low frequency. And the problem that we have is if we do that, then this green signal and this black signal, if they multiply together, they will also give a component at the sum of these frequencies. And now you might say, well, who cares? Right? What if? Let's say, again, I have this signal at 10 gigahertz, and I want to shift it to 5 megahertz. So I multiply it with a signal of 9.995 gigahertz. Okay, so I get my 5 megahertz, and I get 19.995 gigahertz. Who cares about the 19.995 gigahertz? I can very, very easily get rid of that with a very, very relaxed filter. So why get upset and spend so many minutes of a lecture with so many bright students talking about this if it's not a problem anyway? Well, basically that's because it is a problem. And it's not a problem that we multiply this and this and we get to 19.995 gigahertz, because that is indeed easily filtered. The problem is that there can also be interferers. And these interferers, they're always red. And these interferers, if they are at, let's say, 9.990 gigahertz, and I multiply the interferer also, because I cannot separate that, if I multiply that also with 9.995, then this red interferer will also end up at 5 megahertz. And that is a problem, because now I cannot distinguish anymore between my interferer and my green wanted signal. And as we know, and it's not drawn here accurately, but as we know, the red interferer is always stronger, right? That's Murphy's law. It's really a problem to have that on top of my wanted signal. This is what we call the image problem. We have, whenever we do frequency conversion, we have an image which you can think of as a mirror image of the wanted signal in the local oscillator signal. This image basically ends up on top of my wanted signal. And that's really a problem. And so the only way to solve that is to, before I do frequency shift, to have a filter that passes my wanted signal but suppresses my interferer. And only then I can do a frequency shift and I don't suffer from this red signal being on top of the green one. Okay, so far so good. Any questions about this part? But you see that things are already becoming uncomfortable, right? Because we are frequency shifting because we want to have a filter at this low frequency that's easy to avoid having a filter at high frequencies, because that would be difficult. But now we find we need anyway a filter at high frequencies in order to suppress this image. So this whole business of frequency conversion, or frequency shift, it helps somewhat, because we still have an easy filter here, but we don't get completely rid of this filter. But this filter now doesn't have to only pass the wanted signal. This filter is now more relaxed. It only needs to suppress the image. So this is called an image reject filter. And usually the image is further away from the wanted signal than other interferers. And so this filter can be a lower Q, can be more relaxed. And in fact, that gives us an interesting trade-off. Because how far away is this image? Well, the distance between this image and the LO signal is the same as the IF frequency. And it's the same as the distance between the LO frequency and the wanted signal. So the difference, frequency difference between the wanted signal and the image is twice the IF frequency. So if I want to have a relaxed filter here, relaxed image reject filter, I want a high IF frequency, because that moves the wanted signal and the image further apart and makes this filter easier. But the higher IF filter, IF frequency, excuse me, makes the IF filter more difficult. So if you look at that, we end up with a more relaxed filter here and an easier filter at low frequency. But it depends quite a lot on, on the IF frequency, right? Because if I make the IF frequency higher, then this filter becomes more difficult because it moves to higher frequency. But this filter can become more relaxed because my image is further away. So, is there anything we can do about that? Well, so let's get back to this. What would happen if instead of moving this IF frequency higher, we would move this IF frequency lower? What if we would move this IF frequency to 0? Then my LO frequency would be the same as my RF frequency. And my interferer, my image, would be myself. So there is no image anymore. Then life is good, right? Because that's great. I don't have to worry anymore at all about images. There is no image. I'm my own image. So I don't need an image reject filter. Great. And this filter is now a filter around 0 frequency. It's a low-pass filter instead of a bandpass with a Q of 0. Wow. Very easy filter for at IF. No filter at RF. This must be great. And indeed, when you look in literature, this concept of 0 IF, there have been tens of thousands of papers written about it because people are so excited, because it's so great, it will solve so many problems. And you can think that, okay, then apparently we can settle on a single architecture because that's it, right? Well, almost. If I do 0 IF, basically what I do is I do my filtering now as low pass. And we can do that. All of that is true. We don't need a filter here anymore. But now I have the problem that my green signal is partly in the negative frequency domain and partly in the positive frequency domain. So half of my signal power is at negative frequencies and half of my signal power is at positive frequencies. And sometimes I don't care. Right? If I have, for example, a signal that's on-off keying, where I represent the 1 by transmitting a signal and I represent the 0 by not transmitting a signal, I don't care whether this is in the negative frequency domain or the positive frequency domain. I only want to detect whether there's energy, and whether it's positive or negative frequencies, I don't care. Same with amplitude modulation. In fact, any spectrum that's completely symmetric, where the same information is on the negative frequencies as positive frequencies, great, I don't have to worry about it. And that's true for many systems. However, if you want to efficiently use your spectrum, and you might remember from the first lectures that I got quite excited about efficiently using the radio spectrum, because we all share that, all the radios share that, and we get more and more radios, and so we have to be very efficient and not use more of the radio spectrum than we need. Transmitting the same information twice, one on the negative frequencies and one on the positive frequencies, is not an efficient use of the spectrum. So with more and more modern systems, we see that's not the case, and there's different information in the left half and the right half of the spectrum. And now we need to be able to separate that. And so we need to be able to tell whether part of the spectrum that we get is a positive frequency or a negative frequency. And how do you do that? How do you know whether a signal that you see is a positive frequency or a negative frequency? And now I wanted to show something that I cannot easily show on this laptop. So let's do it differently. Let's look at this sine wave. Is that a positive frequency or a negative frequency? Why? Yeah? Yeah? So we assume that this is t equals 0. And so we could say that since this is going up first, this could be a times the sine of omega t. And indeed, it goes up first from t equals 0. Yeah. No, I don't have that slide. However, I could also argue that this, let's say this amplitude is 1, right? So this could be either 1 times this, but I could also say it's minus 1 times the sine of minus omega t. Right? So I could also say this is a negative frequency with a negative amplitude. And what if it doesn't start at 0? What if I have a signal that starts like this? How can I tell? Anyway, if I have a signal, right? I have a signal generator. I measure what's coming out. How do I know where t equals 0 is? Who tells me? I mean, if we're serious about that, t equals 0 happened some 4 billion years or 6 billion years ago or so, right? When there was this Big Bang. But we don't know it to the nanosecond accurately. So for gigahertz signals, that this is not really helping. So we don't have a time reference. We don't have an absolute time reference that tells us when t equals 0. And that makes it really hard to say whether a signal is a positive or a negative frequency. You could make another argument. You could also say that this is positive amplitude and a positive frequency, a negative amplitude and a positive frequency, but just traveling backwards in time. Also gives the same signal. Yeah, I would have to draw it the other way, right? So I would have to draw it like this. But in the end, it looks quite the same. So without any additional knowledge, there's just no way that you can tell whether a signal is positive or negative. You need to know something. You need to know where t equals 0 is. Or you need to know something extra. So how do we do that? Well, in reality, in radios, we have this requirement. Right? If we do 0 IF, we want to distinguish positive and negative frequencies, so we need somehow to have the equivalent of a marker that says t equals 0. And the way we do that is by describing the signals in the complex domain. So rather than describing it just as a sine wave, we say, no, it's actually a complex number, an amplitude times e to the power of j omega c t plus some phi. So the sine wave we model with an amplitude and a phase. And we consider that as rotating around as a function of time. And now we can tell whether it's a positive or a negative frequency, because if it's rotating this way, it's a positive frequency. If it's rotating that way, it's a negative frequency. But of course, this gives us another problem, because if I have a piece of wire, how can I see which way this is rotating? You still cannot tell. The way to solve that is to have two wires. One wire where we carry the real part of this vector, and one wire where we carry the imaginary part. And we call this wire, for historical reasons, I, and this wire we call, for historical reasons, Q. And what you get is, it would be nice to have a marker, but I guess if this is time, and I have my I signal and my Q signal, then this is, if I have a circuit like a signal like this, then I would draw this as starting with I equals 0 and Q equals 1. Then Q decreases and I increases. Right? So I'm going this direction, and I get this circle, so my amplitude phase vector turns around in this direction, and this means I have a negative frequency. If I had a positive frequency, then positive frequencies by definition are purple, because that's the color that I have here, and it would be like this. So by having two signals, I can look at the phase difference between these two signals, and the phase difference basically tells me whether I'm rotating clockwise or counterclockwise, and tells me whether my frequency is positive or negative. So by splitting my complex signal into two signals, one signal, the I signal, which is the real part of the complex signal, and the Q signal, which is the imaginary part of the complex signal, I can reconstruct the complex signal because I know its real part and its imaginary part. And from complex signals, I can tell the difference between positive and negative frequencies because I can tell which way they're rotating. Now, this might seem still rather abstract, but the good thing is we are close to something that's electronic again. So, if we, okay, I'm going to, if you look at the 0F receiver, then we have, normally we have this one multiplication, but what we do instead is we split the signal and we multiply the input signal, the RF signal, twice. Once we multiply it with the sine of the LO signal, and one with the cosine of the LO signal. And if we do that, then this gives us a frequency shifted part of the input signal that is the real part of the input signal, and this gives us a frequency shifted part that is the imaginary part. So we now have a way to generate these two signals. One is the real part, one is the imaginary part. Together they give a complex representation of the input signal. And that's nice because that means that if I have now the same problem, that I have a green wanted signal and a red interferer and at the image frequency, then both of them will end up at the same frequency, but one of them will rotate clockwise and the other one will rotate counterclockwise. So now I can tell them apart. And in 0IF, my interferer is myself, but now I can distinguish whether my immediate frequency of my input signal is positive or negative by just observing whether I'm rotating my complex signal in a clockwise or counterclockwise way. And that's nice because now 0IF actually works. Now I can even use 0IF for signals for which the negative part of the spectrum, negative frequency part of the spectrum, and the positive frequency part of the spectrum that's being transmitted are different because I can distinguish them in the I and Q domain. The price you pay is that you need now two frequency shifts, and everything that's after the frequency shift, after the frequency conversion, you also need double. So if you have filters there, well, then you need two filters. But that's the only price you pay. The advantage is that you can now mix directly to zero. These filters can now be low-pass filters, very easy ones, and you don't need an image filter. So, great, right? So you're back where we were. We're happy again. We're smiling because we have this concept of 0IF that seemed to solve all problems because I don't have an image anymore. Then we got into trouble because we could not distinguish positive and negative frequencies in my wanted signal. But we have a solution for that as well. So life is great and everybody does 0IF. Or not. There are still things. There are disadvantages. We don't have an image. We have a very simple IF filter. For that reason, we can integrate everything. We can integrate the filters, the frequency conversion, the amplifiers, everything. It's simple. It's cheap. Makes everybody happy, except what if this splitting in two parts, one with the real part and one with the imaginary part, what if that doesn't work perfectly? I assume in the splitting that I have my LO signal in two versions. One as a sine and one as a cosine. What if these two versions are not exactly a sine and a cosine? What if one is a sine, but the other is a cosine with a slight phase shift? In that case, I decompose my signal not on two orthogonal axes, I and q, but on two axes that are not quite orthogonal, and so I get a phase mismatch. And for the same, in the same way, I can also have that one part, the LO signal, there might be perfectly a sine and a cosine, but one might be slightly larger amplitude than the other. And so I might have a base in which I have an amplitude mismatch. And if that happens, then you can do some easy analysis, but you can easily see that I can now decompose this wrong vector into a vector that is compensated by an arrow vector, and that arrow vector, if I decompose to that, then I get an input signal that consists of two parts. One part that is decomposed correctly in I and Q, and one part that is what we call leaking, that's decomposed with the wrong sign of the frequency. So if I have an amplitude and phase mismatch, and I put in an input signal, and I'm looking at the positive part of the spectrum, then I should have a signal that completely rotates this way. But if I have a small mismatch here, then mostly it rotates this way, but a very small part rotates the other way. So I cannot perfectly distinguish anymore between positive and negative frequencies, and I get some leakage between these two parts. And you can easily calculate that, and you can see that this leakage depends on the amplitude error and the phase error that you make. The larger the phase error, the larger the amplitude error, the larger the leakage. So you can see that here, if you have a phase error of 3.5 degrees, 3.6 degrees, or an amplitude error of 6.4%, then 1/1000th of the power at positive frequencies leaks to negative frequencies, and vice versa. If I want less, if I want to have only 1/10,000th of the power, I need to have an amplitude error of 2% or a phase error of less than 1.2 degrees. And when you think about it, these are small numbers. If you have 10 gigahertz, that means that one period is 0.1 nanosecond, 100 picosecond. That's 360 degrees. If I want 1 degree error, then I have 100 picoseconds divided by 360. I have a timing error of 0.0, I'm saying that correctly, 0.2 picoseconds. 0.2 picoseconds at the speed of light, 3 times 10 to the power of 8, times 0.2 times 10 to, I need to write this down, sorry. So we have 0.2 picoseconds times the speed of light, 3 times 10 to the power of 8 meters per second. So we have 0.6 times 10 to the power of minus 4 meters. So that is 60 micrometer length. If the cables with which I connect the I and the Q signal of the local oscillator are different in length by 60 micrometers, I already have this leakage. Now, if you ever look at the cable in the lab, and especially the way that most students deal with cables, then even the accuracy with which you screw the cable connector onto the plug can easily change by more than 60 micrometers. If you turn a little bit stronger, then already you get the cable to be shorter by more than the 60 micrometers. For that reason, in the lab, we use special torque keys to reproducibly connect connectors always with the same force, and so always with the same length. Even so, 60 micrometers is very, very small. And if you go to higher frequencies, this number gets smaller. Obviously, it scales with frequency. And that means that for 0 IF, there's almost no choice. You will have to build in some calibration to fix this, because you cannot, by design, achieve this level of accuracy. Another problem of 0 IF. You now have a local oscillator signal that's at the same level as the same frequency as your antenna signal. by definition, right? Because we want to shift to 0. So we have a 10 gigahertz antenna signal at, let's say, 1 picowatt, and we have a 10 gigahertz oscillator signal, but at a higher level because we need to drive this mixer. And to drive a mixer, you need in the order of 1 milliwatt, which is about 10 to the power of 9 stronger. And these things are on the same IC at a distance of less than 1 millimeter. So we will have to realize more than 90 dBs of isolation between my oscillator and the antenna input. Otherwise, the crosstalk of my oscillator to the antenna will be stronger than the signal I'm looking for. Which is highly annoying, because we just got rid of this interferer, and what we get back for it is our own interferer that we make ourselves. That's not nice. That's another problem of 0IF that needs to be solved, partly through careful design, by having good isolation, but at these frequencies this isolation is never going to be good enough. So on top of that, you will need to build in, again, some compensation and calibration. But you might think that these things are manageable, but there's more. Right? What if I have a strong interferer, and what if this interferer is AM modulated? And what if somewhere in my receiver, in the amplifiers or in the frequency conversion, I have second order distortion? Well, if this is a sine wave, this interferer, then that sine wave, through the second order distortion, which is a quadratic term, will give a DC component. And something at twice the frequency, but we don't worry so much about twice the frequency. But we do worry about the DC component, because the DC component is exactly at the middle of the IF frequency that we're trying to receive. If it's modulated, well, we get a modulated signal exactly in the middle of the signal we're trying to receive, independent of the frequency of the interferer. Boy, you know, you think you have solved something, you get 10 problems back. But this is what happens. So I've been arguing that you don't need an image reject filter in 0IF, and that's still true. But you do need a filter that suppresses very strong AM modulated interferers to a level where, in combination with the second order distortion, you don't get so much modulated DC that it interferes with your wanted IF signal. And that means you have to have some filtering still, and you need a very good second order distortion, second order linearity. How do you achieve second order linearity? Anybody have an idea? And you go to an experienced designer, of course. That's how you start. But what is he going to tell you? It's something we'll come back to later when we talk about circuits, but good for you to realize already. When you have a circuit, and you would duplicate that circuit. So, I have a circuit, and there can be all kinds of stuff in. We don't know for sure, but there's all kinds of stuff in this circuit. If I duplicate that, and we assume that they're exactly identical, but that they have significant second order distortion, each of them. Now, if I take my input signal here and I invert that, right? So I make this times -1. And at the output, I subtract them again. What happens is that the second order distortion here and the second order distortion there, they're the same, right? Because even though the sign at the input has changed for this and that one, since I have a squared function, they both, the distortions both become positive, right? Whether the input, if the input signal here is 1 volt, I get squared, it's 1 volt. Here it becomes -1 volt, but get squared is 1 volt. I subtract them, the second order distortion disappears. But my signal doesn't disappear, because my input signal gets amplified. Here my negative input signal gets amplified and gets subtracted, and so I subtract a signal from its negative self, so I add it to itself. So my signal remains, and my second order distortion disappears. Isn't that great? And in fact, that trick works with every even order distortion. So whenever you need to have good even order distortion, just make the circuit twice and feed the signal and the inverted a copy of the signal through both paths, subtract the outputs, and you get rid of second order distortion. This is called the balanced circuit, and we'll come back to that in the future. This brings me to the end of this lecture. There's further disadvantages of zero IF, but they're easier to understand. So I would recommend that you read through them and also through the remainder of the slides, because they talk about some other architectures. But once you've understood the concept of frequency shift, of the balancing of gain and linearity and noise, then the other architecture should become self-explanatory. If you have any questions about that, I will be available next Monday on Skype at the usual time, even though it's Carnival, don't worry. Even though I'm from Limburg, I'm not celebrating Carnival, so I will be as sober as I'm usually. The Monday after that, unfortunately, I will be in California, and so during the time that there is the normal time for the Skype session, it's normal office hours there, and I will be at the conference. So not coming Monday, but Monday after that, I'm not available for Skype. Okay? But you can always ask questions by email, and I will try my best to answer them. So request then is to take one of the 3 assignments that are now on OASE, select one with your team, and for the next period, so over 2 weeks, please prepare the system design, the architecture, and the circuit specifications for that assignment for your chosen implementation as a team. It doesn't have to be perfect, because we still have many lectures to go, but I think it's good to start and to have a discussion. In 2 weeks, I will ask some of you to present what you have found, and then we will discuss it and see what things that I should have explained better. Okay? Thanks a lot. Have a nice Carnival, and see you in 2.5 weeks.